Yes. So, very good morning to you all. I welcome you all for today's EMF session. In my last class, I have discussed just a minute. Yeah. So, in my last class, I have discussed about potential due to a dipole, right? Um, a dipole. So, what is meant by a dipole? Two point charges separated by a distance d, right? It is called as a dipole. And we have determined potential at a point P with respect to a dipole. A dipole is considered along z-axis, and potential at point P is determined, right? So as we are considering a dipole in the sense plus q and minus q are separated by distance d, and the potential at point P is the potential at plus q and the potential at minus q, which was given in equation 2. You can see here. And R1 and R2. R1 is the distance from point A to point P, and R2 is the distance from point B to point P. R1 and R2 are determined from the figure in terms of R theta. They are substituted and simplified. So simplifying, you will get this one. V is equal to QD cos theta by 4 pi epsilon naught R square. That is the potential due to a dipole. If you know potential due to a dipole, we can determine electric field, right? We can determine electric field. So because we know the relationship between electric field and potential, substituting potential, simplifying, and we will get electric field due to a potential, right? And afterwards we have done problems related to potential. When a potential was given, we have seen how to determine electric flux density, and also we have seen how to calculate work done, right? Work done in moving a point charge from one point to another point, that we have seen. So today we are going to see another very important topic called energy density, right? So energy density, or um, energy stored in an electric field. Energy stored in an electric field. How much energy electric field can store, that we are going to calculate now. And as we know that EM wave. So what is the importance of EM wave? EM wave carries information from one point to another point, right? EM wave carries information from one point to another point. EM wave carries information from one point to another point in the form of energy. In the form of energy, right? So therefore, how much energy electric field stores? EM wave in the sense which is a combination of electric field and magnetic field. How much energy electric field stores and how much energy magnetic field will stores. If we add those two, we will get the total energy stored in EM wave, or the total energy that can carry by an EM wave that we can calculate. So in this chapter, we will determine energy carried by electric field, and in the next chapter, we will determine energy carried by magnetic field. To determine energy stored in an electric field, let us consider an initially a charge-free region, right? Let us consider an initially a charge-free region. So let us say this is initially a charge-free region. Charge-free region in the sense what? The electric field is zero. There is no electric field in it. There is no electric field in it, right? So no electric field in the sense what? No charges inside this region, right? So now what I will do is from infinite distance. So let us say so this is an infinite distance. So from infinite distance, I will try to move a point charge, right? I will try to move a point charge Q1 to point P1, right? From infinite distance, I'm moving a point charge Q1 to point P1, right? So point P1 is the region where initially charge-free region. Let us consider an initially charge-free region, right? So our aim is to you just keep this in mind. Our aim is to determine work done or energy, both are same, right? Work done in moving point charges from infinite to a region, this region, right? So here I will try to move number of point charges, right? Number of point charges. So if Q1 is moved from infinite to point P, what is the work done? The work done is zero. Why work done is zero? Because this region is initially charge-free region, right? This region is initially charge-free region, right? So whenever this region is initially charge-free region, then charge-free in the sense what? No electric field. When there is no electric field, no work needed to move a point charge Q1, or no energy needed to move a point charge Q1, right? So therefore, work done in moving a point charge Q1 to an initially charge free region is zero, right? Now I will try to move another point charge, right? I will try to move another point charge Q2 to point P2, right? I'm trying to move another point charge Q2 to this region, into this region. Now what is work done? Work done is not zero, right? Work done is not zero. Why work done is not zero? Because already Q1 we have placed inside the region, right? Already Q1 is there. So whenever Q1 is there, electric field exists. Whenever electric field exists, work done to move a point charge requires some energy, right? Work done in moving a point charge is not zero, right? So therefore, work done work done in moving a point charge Q2 to point P2 is Q2 V21, right? Q2 V21. So this is the work done in moving a point charge Q2. That's because we know that work done W is equal to, right, minus Q integral V dot dl. So this is the work done, and this we know earlier we have seen this, right? Sorry. W is equal to minus Q integral E dot dl, right? Q E dot dl, and this is equal to QV, right? W is equal to QV, since V is equal to minus integral E dot dl, right? So therefore W is equal to QV, right? So work done is QV, right? So therefore when a point charge Q2 is positioned at P2, the work done is Q2 V21, right? Where V21 is potential, right? Potential at P2 with respect to Q1, right? Potential at P2, potential at P2 with respect to Q1. That's because already Q1 is placed, right? So therefore, potential difference with respect to Q1, that potential is called as V21, right? So V21 is the potential at P2 with respect to Q1. Now, another third point charge, right? I'm trying to move another point charge Q3 at a point P3, then the work done, right? Work done in moving a point charge Q3, work done in moving a point charge Q3 to a point P3 is Q3 V31 plus V32, right? So this is the work done. V31, what is V31? V31 is the potential at point P3 with respect to Q1, and V32 is the potential at point P3 with respect to Q2, right? So because before placing Q3, already Q1, Q2 are there, right? Before we place Q3, already Q1, Q2 were there, right? So therefore, potential with respect to Q1 and Q2, right? With respect to Q1, in other words, so potential due to Q1 and Q2, right? Therefore, total work done WE, right? Total work done, right? In the presence of electric field, right? Is given by, so what is the total work done? Work done in moving a point charge Q1 is 0. Work done in moving a point charge Q2 is Q2 VT1 plus work done in moving a point charge Q3 is Q3 V31 plus V32. And let us say this is equation 1, right? So this is the total work done in moving a point charge, right? So now let us reverse. Now let us reverse the order, right? Now let us reverse the order, right? So reverse the order in the sense what, earlier Q1 is placed at P1, and then Q2, and then Q3. Now I will place Q3 first, right? I will place Q3 first. Then what is work done is 0, right? Because initially charge free region, right? So when it is initially charge free region, the work done in moving a point charge Q3 is 0, right? So therefore WE is equal to 0 plus now Q2, right? Q2. So what is work done? Q2 V23. Got my point? Q2 V23, right? So where V23 is the potential at point P2 with respect to Q3, right? Because Q3 is placed initially. Q3 is placed first. In the second case, Q3 is placed first. So similarly, if Q1 is placed, right? If Q1 is positioned at P1, then the work done V1 is equal to V12 plus V13, right? So this is the total work done, right? So equation 1 and equation 2 are same. Even though the order is reversed, the work done, if you calculate the work done, you will get the same, right? You'll get the so therefore, to simplify this, right? So it can be simplified by doing some mathematical manipulations, right? So adding equation 1 and 2, right? Adding equation 1 and 2, right? So adding equations 1 and 2, we will get, right? So adding equations 1 and 2. So adding equations 1 and 2, what we'll get on the left hand side, we have WE. So therefore 2 WE on left hand side we have, right? So this is equal to adding this, what we'll get, Q2 V21 plus Q2 V23 plus Q3 V31 plus V32 plus Q1 V12 plus V13, right? So this is equal to writing in an order, Q1 V12 plus V13 plus Q2 V21 plus V23 plus Q3 V31 plus V32, right? So 2 WE, right? So this is equal to WE, this is the work done, and 1 by 2 into Q1 V12, let us say Q1 V1 plus Q2 V2 plus Q3 V3 plus here, just for an example, I have considered only 3 point charges, Q1, Q2, Q3. If n number of point charges were considered, then Q1 V1 plus Q2 V2 plus Q3 V3 plus Q4 V4 plus and so on, right? And so on. So therefore, and so on, right? And so on, right? And here where V1 is equal to what? V1 is equal to V12 plus V13 plus and so on. If n number of point charges were considered, it will be sequential like this. And V2 is equal to V21 plus V23, and V3 is equal to V31 plus V32, right? So this is the total potential at point P1. So this is the total potential at point P1, and this is the potential at point P2, and this is the potential at point P3 with respect to the other point charges, right? With respect to the other point charges. So this is just like applying superposition theorem, right? So superposition theorem, we will determine potential um, by the sum of potential due to the other sources, right? So here we do the same, right? So therefore, summarizing, we is equal to 1 by 2 summation k is equal to 1 to n q k v k, right? So this is the work done, right? Or energy density, right? Work done or energy density when point charges are considered, right? When point charges are considered, right? Let us say this is equation 3, right? When point charges were considered. So therefore, when point charges were considered, the total work done or energy density is given by half summation k is equal to 1 to n qk vk. Very simple, right? But if we consider continuous charge distribution, right? If we consider continuous charge distributions, what is meant by continuous charge distributions? Line charge, surface charge, and volume charge, right? So if we consider a continuous charge distributions, right, then equation 3 become, we know that, right? So just may recollect this. We know that for a line charge, what is q? Q is equal to line integral rho l dl. And similarly, if it is a surface charge, then q is surface integral rho s ds. If it is a volume charge, then volume integral rho v dv, right? So here, when continuous charge distribution, right, when continuous charge distribution is considered, then the summation here will be replaced with integral, right? So when continuous charge distribution is considered, then summation is replaced with integral, right? Summation is replaced with integral. Then because we know that q is equal to integral. If it is a point charge, we add up all the point charges, right? But whereas it is a continuous charge, then integrating, right? Then integrating, right? So therefore, considering, so for example, I will consider a volume charge instead of line charge, surface charge. Let me consider, right? Let us consider, let us consider a volume charge, right? Let us consider a volume charge, right? So for a volume charge, we know what is q. So q is equal to volume integral rho v dv, right? So therefore, work done we is equal to half volume integral rho v into v dv, right? So generalizing this, right? So rho v into v, right? So here only q is replaced, right? Q is replaced with this. So q is replaced with this, right? And we have already v, right? We have already v, right? So therefore, v is the potential, right? And let us say this is equation 4, right? So therefore, if we consider a volume charge, then work done w is equal to half volume integral rho v into dv, right? And further simplifying this is equal to half volume integral delta dot d into v dv, right? Let us say this is equation 4, 5. Since delta dot d bar is equal to rho v, right? So this we know. So this is the first Maxwell's equation which we have discussed earlier. Therefore, replacing rho v with delta dot d, right? So now, to simplify further, right? To simplify further, here the term delta dot dv, right? The term delta dot dv is one vector identity, right? So from one vector identity we can write like this, right? From vector identity, what is that? Divergence of d and v, right? Divergence of d and v, right? Divergence of d and v can be expanded like this, right? So let me write this: divergence of v and d d dot delta v plus v into delta dot, right? So this is the expansion, right? So one vector identity, divergence of, and here divergence of product of d bar. What is d bar? D bar is vector. And what is v? V is potential, which is a scalar, right? Which is a scalar, right? So therefore, divergence of product of vector and scalar, divergence of product of vector and scalar, the expansion is this one, right? Expansion is this one, right? So from this we can write, from this we can write v into delta dot d bar is equal to delta dot d bar v minus d dot delta v, right? And let us say this is equation 6, right? So because we require this term, right? We require this term. So therefore, this is equal to, right? So this is equal to taking this term to the other side, and we have this one, right? So therefore, from equation, from equation 5 and 6, right? From equation 5 and 6, that means what? Substituting equation 6 in equation 5, right? Substituting equation 6 in equation 5, we have this we we is equal to half volume integral. So delta dot d into v is what? Delta dot d bar into v minus d bar dot delta v dv, right? And further simplifying, so further simplifying this, we is equal to half volume integral delta dot d bar into v minus, sorry, dv minus half volume integral d bar dot delta v into dv, right? And let us say this is equation 7, right? So this is equation 7, right? So now here applying here in equation 7 to the first term, applying applying divergence theorem, right? Applying divergence theorem to the first term of equation 7, applying divergence theorem. So as we know that divergence theorem will give the relationship between surface integral and volume integral, right? So therefore volume integral can be converted into surface integral, right? So doing that, we is equal to half surface integral d bar v dv minus half volume integral d bar dot delta v dv, right? So let us say this is equation 8, right? Since surface integral d bar v ds, sorry, here ds is equal to volume integral divergence of d bar v dv, right? So this is the divergence theorem, right? So now here again in this first term, right? So in this first term, so in the first term here d bar, so what is d bar here? D bar is equal to q by 4 pi 4 pi r square ar bar, and what is v? V is equal to q by 4 pi epsilon naught r, right? 4 pi epsilon naught, right? And ds 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 is r square, right? ds is r square, right? So therefore d bar is this, and v is this, and ds is r square, right? So therefore from this we can say that d bar is proportional to 1 by r square, and v proportional to 1 by r, and ds, right? ds is proportional to r square, right? Proportional to r square, right? So therefore d bar v ds multiplying, right? Multiplying these two is proportional to 1 by r, right? So 1 by r square, 1 by r into r square, so it is 1 by r, right? So therefore d bar v into ds is proportional to 1 by r square, right? So as r tends to infinite, as r tends to infinite, because we are moving a point charge from infinite distance, right? So as r tends to infinite, then 1 by r will be 0, right? 1 by r will be 0. So therefore the first term in the right hand side of equation 8 will be 0, right? Will be 0, right? So therefore this will become 0, this term, right? So this term will become 0, right? So keeping that 0, we will get, so we will get we is equal to minus half volume integral d bar dot v dv, right? And further simplifying this, minus 1 by 2 volume integral d bar dot v. So what is v? V is equal to minus, here v is equal to minus what we can write here, we know the relationship between um, okay, okay, sorry, it is delta v, right? I have forgotten to write delta v. D bar dot delta v dv, right, from equation 8, right? So therefore this is equal to minus half volume integral d bar minus e bar dv. Since e bar is equal to minus delta v, right? And further simplifying, half volume integral epsilon naught e square dv, right? Since d bar is equal to epsilon naught e bar, right? D bar is equal to epsilon naught e bar, and minus will get plus, and substituting d bar is equal to epsilon naught e, and we have half volume integral epsilon naught e square, right? Epsilon naught e square, right? So this is the work done, right? So therefore joules units are joules, right? So therefore we, right, we is equal to half epsilon naught um, volume integral epsilon naught e square dv, right? So this is the work done, right? Work done, or energy stored in an electric field, right? And as we know that the field is uniform, right? Field is uniformly distributed, so therefore epsilon naught e square can be taken outside, right? Epsilon naught e square can be taken outside, or in other words, right, in other words, delta we, is equal to half epsilon naught e square um, delta, right? Differentiating, delta we is equal to half epsilon naught e square delta v, right? So therefore delta we by delta v is equal to half epsilon naught e square joules per meter cube, right? So this is joules, right? This is joules, but whereas this one is joules per meter cube, right? Joules per meter cube, right? And we, right? We small letters, right? Small letters, half epsilon naught e square, right? So this is the final expression, right? Joules per meter cube, right? So sometimes in examination they will ask you to determine energy stored in electric field or energy density in terms of joules per meter cube, right? So this is the final answer, right? So therefore the total energy, so this is nothing but the total energy stored in an electric field, right? In an electric field is half epsilon naught e square, right? Is the energy stored in electric field, right? So this is how we can calculate energy stored in an in a electrostatic field, right? So let me explain once again, so because this is very important topic, right? So energy density, right? Energy density or energy stored in an electric field, energy density or energy stored in an electric field, right? So let us say this is the initially charge free region, right? Initially charge free region, right? Let us consider initially charge free region. So charge free in the sense what? No electric field. Electric field is zero, right? So when electric field is zero, moving a point charge, no work done, no energy is required to move a point charge, right? So therefore, moving a point charge Q1 to an initially charge free region is zero. Now, work done in moving another point charge Q2 to point P requires energy. Why? Because already Q1 is placed, right? So already Q1 is there. So therefore, electric field will be developed. When there is electric field, we need energy to move Q2, and that energy is Q2 V21, and where V21 is the potential at point P2 with respect to Q1. And if you move another point charge, third point charge Q3, the energy required, right, or work done is Q3 V31 and V32, right? Q3 V31 plus V32. So total work done in moving 3 point charges is equation 1, right? So equation 1 is the total work done in moving 3 point charges, right? So now let us reverse the order. So earlier I have placed Q1 and then Q2 and then Q3. Now reverse order. That means initially Q3, then Q2, and then Q1, right? So if I do so, the total work done is equation 2. In a similar procedure, if you calculate, the total work done is equation 2. So therefore, adding equation 1 and 2, and 2 WE is equal to this, you will get, and simplifying this, right? Simplifying this, and we have this one half Q1 V1 plus Q2 V2 plus Q3 V3 and so on. If there are more than 3 point charges, you go on adding sequentially, you will get the total work done, right? So where V1 is this, V1 is equal to V12 plus V13. For example, if there are 4 point charges Q1, Q2, Q3, Q4, then what is V1? V1 is V12 plus V13 plus V14. If there are 4 point charges. Similarly, V2 is equal to V21 plus V23. If there are four point charges, then V21 plus V23 plus V24 and so on, like that. And similarly, V3 is equal to V31 plus V32, right? So summing up this, you can write like this: W is equal to half summation K is equal to 1 to N, where QK VK, right? So this is the total work or energy density or work done with respect to point charges, right? With respect to point charges, right? So if we consider continuous charge distributions, so what are the continuous charge distributions? Line charge, surface charge, volume charge, like that, right? So then Q is replaced like this, right? So let us consider a volume charge, then Q is replaced with this one. Q is replaced with this. Here, Q is equal to volume integral rho v dv. So therefore, substituting that, and we will get this one. And from vector identity, right? So divergence of product of vector and scalar. The expansion is this one. So from this, we require this term, right? We require this term, and so because here we have this term, right? So therefore, finding out this term, we have equation 6. So substituting equation 6 in equation 5, we will get this one, right? And we know that, right? So we know that d bar here again applying divergence theorem. So divergence theorem is used to convert volume integral into surface integral, this one. And d bar, we know electric flux density, which is proportional to 1 by r square. V is potential, which is proportional to 1 by r, and ds is area of surface. So proportional to r square. So product of these three is proportional to 1 by r. And as r tends to infinity, 1 by r will be 0, right? So therefore, the first term will become 0, and we are left with this one, right? We are left with this one, right? And simplifying further, E bar is equal to minus delta V. So here, substituting here, and D bar is equal to epsilon naught E bar, substituting it here, and simplifying, you'll get this. And this is in terms of joules, right? And differentiating this and taking the volume to the left hand side. So WE by volume, that means joules per metric cube. Volume in the sense metric cube, right? So per unit volume, right? So this is the final equation. So total energy stored in an electric field is half epsilon naught E square, right? So number of times this question was asked, right? So prove that the energy stored in an electric field is half epsilon naught E square, right? Like that the questions were given, right? So with this we have completed energy density. Related problems, let us see one or two problems. So we have 10 more minutes time. So let us see as many, maybe one or two problems we will see, and then we will close the session, right? 3-point charges, -1 nanocoulomb, 4 nanocoulomb, and 3 nanocoulomb are located at 0, 0, 0, 0, 0, 1, and 1, 0, 0 respectively. Find the energy in the system, right? Find the energy in the system, right? So we need to determine energy, right? We need to determine energy. What is given? Point charges, right? What is given? Point charges were given, right? So 3-point charges were given, right? 3-point charges were given. So therefore, with respect to point charges, what is energy? WE is equal to half summation K is equal to 1 to 3 QK VK. With respect to point charges, you need to see carefully the problem, right? Whether a problem contains point charges or continuous charge distributions, that we have to see. So in the problem, point charges were given, right? So as point charges were given, we have to take this equation, right? We have to take this equation. If continuous charge distribution is given, then we have to take this equation, half volume integral epsilon naught E square dV, right? So this is the equation for continuous charge distribution, right? And this is the equation for point charges, right? When point charges were given, we have to consider this equation, right? So therefore we is equal to half q1 v1 plus q2 v2 plus q3 v3. Let us say this is equation 1, right? So q1 is given, q2 is given, q3 is given, right? Q1 minus 1 nanocoulomb, q2 4 nanocoulomb, and q3 3 nanocoulomb. It was given in the problem, right? So only thing is we have to calculate v1. So what is v1? V1 is equal to v12 plus v13. And what is v2? V2 is equal to v21 plus v23. And similarly v3 is equal to v31 plus v32, right? So therefore v12 and v13, right? So v1 is equal to v12. So what is v12? V12 is q2 by 4 pi epsilon naught r12 plus q3 by 4 pi epsilon naught r13. So this is v1, right? v12. So what is v12? V12 is the potential at point p1 with respect to q2, right? With respect to q2. And similarly v13 is the potential at point p1 with respect to q3, right? With respect to q3, right? And similarly v2 is equal to q1 by 4 pi epsilon r21 plus q3 divided by 4 pi epsilon naught r23, right? So on v3 is equal to q1 by 4 pi epsilon naught r31 plus q2 divided by 4 pi epsilon naught r32, right? So here in this everything is known, right? So q2 is known, epsilon naught value is known, and we have to determine r12, and we have to determine r13, r21, r23, r31, r32. So what is r21, r12? R12 is the distance between in other words, more clearly, right? More specifically, it is the scalar distance, right? Scalar distance between 1 and 2, point 1 and point 2. So what is point 1? 0, 0, 0, right? And point 2. So what is point 2? What is point 2? Point is 0, 0, 1, right? Point 2 is 0, 0, 1, right? So similarly r13. So r13 is the scalar distance between 0, 0, 0 and 1, 0, 0, so on and so forth, right? So on and so forth. So what is the distance between these two? R12 is equal to square root of what will get 0 minus 0 whole square plus 0 minus 0 whole square plus 1 minus 0 whole square. So this is equal to 1, right? R12 is 1, right? So similarly R13 is equal to 1. You will calculate, you will get 1, so on. right? So calculate R21, R23, R31, and R32, and substitute those values and simplify, right? And from equation 1, if you calculate, right, if you calculate energy substituting all the values, and if you calculate energy, you will get 13.37 nanojoules, right? 13.37 nanojoules. So this is the answer you should get, right? If you calculate substituting and simplifying, calculating, you will get 13.37 nanojoules, right? So this is how we can do the problem, right? So one more problem. This is the problem related to point charges, and in the next class we will consider one continuous charge distribution, and let us close this topic, right? So do remember, within 2 to 3 classes I'm going to complete this chapter, right? So within 2 to 3 classes we are going to complete this chapter, and in the next week in the third class or fourth class we are going to enter into the magnetostatic. Once electrostatic field is over, magnetostatic field is easy. That's because same things we will discuss there. Whatever the topics we have discussed with respect to electric field, same topics we will discuss there with respect to magnetic field, right? So therefore, once you are well aware with concepts of electric field, then it will become very easy for you to understand concepts of magnetic field, magnetostatic fields, right? So with this, let us conclude our session. So thank you very much for your patient listening. Let me stop the live streaming.